Hello, good morning to all of you. Today we will be discussing about the basics of econometrics. By the word econometrics, we mean the measurement of economic variables with the help of statistical and mathematical methods. So, if you ask somebody about what do you mean by econometrics, it usually means economic measurement or measurement of economic relationships with the help of statistical tools. You can define econometrics as application of mathematics or statistics to economic data to lend empirical support to the models that is constructed. And these econometric tools are applied in economic theory, mathematics, and statistical inference are applied to the analysis of economic phenomena such as inflation, output, measuring the relationship between productivity and wealth, measuring the impact of inflation on consumers' standard of living. So, if we just take the simple case of price and quantity demand relationship, which poses a negative relationship, or what we say as an inverse relationship, that can also be studied with the help of this. So when we say that econometric analysis, it especially equips us quantifying or quantitative relationship based on a sound theoretical framework. So the implications of econometrics, when we say that numerical estimates which are based on a well-defined scientific logic helps in prediction and policy making. So whatever theory that we choose where we apply econometrics on, we need to see that the econometric relationship, quantifying relationship between the variables must be based on some sound logic. So these are the eightfold methodology that is used in econometrics. So first what we do is we specify the statement or we frame our hypothesis. The second step, we specify a mathematical model that is suitable for specifying the theory. Thirdly, we specify a statistical or econometric model. Fourth, we obtain the data, and based on the data and the statistical or econometric model that specified, we conduct econometric estimation. In the sixth stage, we carry out hypothesis testing, whatever hypothesis we have framed in the step. Next step, that is the seventh step, is forecasting based on the econometric estimation that is already carried out and keeping in view the hypothesis that we have already framed. And in the last phase, which is at the disposal of the policymakers, is based on the estimation and forecasting to make appropriate policies to attain the target of the objectives. So these are 8 steps to which we are going to discuss a little bit about how we are going to approach these 8 steps. First step, that is statement of theory or hypothesis. If I just draw upon the Keynesian fundamental psychological law of consumption, where it states as a rule and on average to increase their consumption as their income increases, but not as much as the increase in their income. Keynes postulated that the marginal propensity to consume, the rate of change of consumption for a unit change in income is greater than 0, but less than 1. That becomes our hypothesis that the marginal propensity to consume to lie between 0 and 1. The next step, in the very next step, what we do is we specify a mathematical model of the theory if it exists. So we can specify a mathematical model as such y equal to beta 1 plus beta 2x, where beta 2, which is the slope of the equation, that measures the marginal propensity to consume. Here, y becomes your consumption expenditure and x becomes your income. It can be monthly consumption and income, it can be annual depending on the frequency of the data that is collected. Beta 1 becomes the intercept or autonomous consumption in this particular case, and beta 2 becomes the slope or what we say as the marginal propensity to consume. So this is how we specify a mathematical model. The third step is if there isn't any mathematical model, still we can specify a statistical model or econometric model. The difference between the mathematical and econometric model is that mathematical models are always exact. It measures the exact relationship between the two variables, whereas in econometric model we bring in a term called U, which stands for the disturbance term, and this in econometric estimation we say that a relationship between variables are economic, so generally inexact. So there are some variation in the dependent variable which often goes unmeasured or which is not explained by the number of independent variables that we have included in the model. So whatever could not be explained in the regression model is kept under the disturbance term. So if you just go back to the previous consumption expenditure example again, you'll see that besides the income, family size, age of the family members, family's religion, these are all things that also affect the consumption expenditure of a particular household or a family. So this U, which we call as disturbance term, may well represent at all those factors that affect consumption, but are not taken into account explicitly. Fourth step, the procedure involves obtaining of data. The data can be obtained primarily or secondarily, depending on the type of study that we're carrying out. So to obtain the numerical values of beta 1, that is the intercept, and beta 2 slope, variables must be measured in the same units. That is what we have to keep in our mind, that it must be in the same scale. The fifth stage, that is the econometric estimation. We estimate the parameters, that is the beta 1 and beta 2 at. Here, if we say, let us say, based on some data, we have found out that the y hat, that is the estimated consumption expenditure, equal to minus 184.08, which is beta 1 hat, that is the autonomous component of the consumption expenditure. I mean, at zero level of income also, we are borrowing 184 units of money to consume our basic necessities, and the other component is called beta 2 hat times xi, that is xi is your income as we have already discussed before, and here beta 2 hat is equal to 0.7064. So that means this 0.7064 is nothing but the marginal propensity to consume. And your marginal propensity to consume value suggests that mean consumption expenditure went up by about 70 paise for 1 rupee is increase in the real income. If the real income increases by a rupee, then the consumption expenditure out of that incremental rupee increases by close to 70 paise. So if you can express it in percentage term, a 100% increase in income leads to 70% hike in consumption expenditure, mean consumption expenditure. The sixth step, what we do is hypothesis testing, that we have framed this hypothesis earlier, that the MPC value to lie between 0 and 1. And we found the MPC to be 0.70. But before we accept this finding, must inquire whether this estimate is sufficiently below unity or not. As we have already found MPC to be 0.70, the statistical confirmation that we need is that 0.70 is sufficiently below 1. So such confirmation or refutation of economic theories is known as statistical. This is a different branch of statistics. So the next step that involves is forecasting. So while we say forecasting based on the estimated models, let us say if somebody asks you if the government wants the aggregate consumption expenditure to be at a certain specified level 4 years from now, what should be the level of income? So this is how, given one value, the other value can be computed, and that would also help us in designing appropriate policies. That's why the next stage that involves is policy making, policy formulation. So suppose the government believes that consumer expenditure of certain amount will keep the unemployment rate at its current level of about certain percentages. So what level of income will guarantee the target amount of consumption expenditure? Say the government targeted the average per capita consumption with amount, let us say 4,000. Then what should be the level of income? So here from, as all the values are given, we can easily find out what should be the per capita income. And as we have found out from the given example, it has come out to be 7197 rupees. So this is what is required for a consumer, for a household to attain consumption expenditure of per capita consumption expenditure, just per capita consumption expenditure of 1,000. Given the MPC is 0.706, which we have computed from the given the time series data. So these were several the 8 major steps through which we achieve an econometric estimation, drawing of references, testing of hypotheses, and finally this is based on the results that we have obtained. So if we talk about the first technique that we apply in econometrics is called ordinary least squares estimation to parameters, and to carry out the Welles regression, to assume something which forms the building blocks for developing a regression model, a sound regression model. So the Welles assumptions are, first assumption would be, let me say that the regression model is linear in the parameters that we have already written in this example. Likewise, it depends on whether it is a multiple regression or a simple regression. So in case of simple regression, we'll have one in, as in case of multiple regression analysis, we will have one dependent variable, multiple number of regressors, or what we say as independent. So linearity in the parameters, when I specify a regression model, the parameters should be linear. It means the highest degree of the parameters should not be in excess of 1. The second assumption that we make about the ordinary least squares regression estimation is fixed values of x. I mean, you can keep in or keep the repeated sampling. I mean, if you do the repeated sampling, x values tends to be fixed in those samples. When I say x values are fixed in repeated sampling, there must be there must be variation within a particular sample of x values. There must be variation in x values within a particular sample, but these values must be fixed in repeated sampling. Third assumption that I make of is mean value of disturbance by ui, which is expectation of ui conditional on xi, the particular given xi. the expected value of ui, that is the disturbance term, is 0. For the disturbance from the original value can be negative deviation, can be positive deviation. So expected value, the mean of those positive and negative deviations comes out to 0, the given conditional x value. The fourth assumption that we'll make, which is rather a very strict assumption, is homoscedasticity. When I say homoscedasticity, this is also a conditional variance of ui, the disturbance term, given the xi, where we say that this must be constant. So at each given xi, the conditional variance of actual y values from its estimated mean value should be same. Conditional variance of ui around its estimated y value, mean y value, should be same at each given xi. This would be important assumption, homoscedasticity, and it is violated many properties of the regression model. The fifth important assumption is what we say as no autocorrelation. When I say no autocorrelation, I mean the disturbance terms at different xi values should not follow a pattern, should not have any kind of relationship. The previous period's ui should not affect the next period's uj. So at different xi values or x values, the u's should not form any kind of correlation. The sixth important assumption that we talk about is zero covariance between xi. That is the disturbance term and the independent value, that is xi. In case of multiple regression, we will have multiple x values. In case of simple regression, we will have only one x value. So this ui and xi should not have correlation. If it is, then the regression, the parameter that is estimated tends to be flawed. Seventh assumption that we make is that the number of observations that we have in our data must be greater than the number of parameters. So including the intercept and slope, partial slope coefficients, our number of parameters should be at least less than the number of observations. The eighth assumption that we'll make is variability in x values. In the second assumption, we said in repeated sampling, the x values are fixed. In eighth assumption, we are saying that within a particular sample, the x values should not be same. Should have appropriate amount of variability. Otherwise, there is no case of finding a relationship between x and y if x is fixed in a sample. So there must be variability in the x values. Besides, the ninth assumption that we'll make is the model specification. We have to see the sort of relationship that exists between the independent values. We should not form an incorrect model. If there is a linear relationship and fit a non-linear relationship to the data, then we tend to estimate a wrong model. So we have to consider in the data what sort of relationship the have between themselves, and according to should form. So this is another important assumption where we will study the repercussions if a model is incorrectly fit or incorrectly specified. Besides, in the 10th assumption, what we have is an assumption of perfect multi-coordinate, and this is more specifically a phenomena associated with multiple linear regression analysis, where we have multiple number of independent variables. The assumption says that if we have multiple independent variables, they should not have a perfect correlation. The correlation between x variables should not be perfect. It should not be. So if it becomes a perfect relationship, then we will be it would be very difficult first of all to isolate the individual impact of different x variables, since there would be a case where one variable acting the dependent variable because of its relation to that. So disaggregating the individual impact of independent variables becomes very much difficult if there is perfect multi-code. So these are the assumptions that we discussed. Besides the assumptions, uh, what we just so based on the assumptions that we specified earlier, the classical definition, the least square estimators, that is beta 1 hat and beta 2 hat, in a simple linear regression model. Among the class of all the unbiased linear estimators, the Gauss-Markov theorem states that beta 1 hat and beta 2 hat as the best linear unbiased estimators. So when I say best, it means the variance of beta 2 hat is the minimum among all the class of unbiased linear estimators. Beta 2 hat is linear, it has highest degree not exceeding 1. Beta 2 hat is also unbiased. When I say unbiased, the sample estimate beta 2 hat, the expected value of that is equals to the population parameter beta 2. So the focus points here is feasibility, distribution of UI, and infeasibility. The Gauss-Markov theorem states that the theorem is remarkable. Why is it remarkable? Because it makes no assumptions. It doesn't put any restrictions about the probability distribution of the random variable. Right? So that is why it is a remarkable theorem, where as long as the assumptions of classical linear regression model are satisfied, the theorem works. If all the 10 assumptions are satisfied, Gauss-Markov theorem says that the estimators beta 1 hat and beta 2 hat are best linear unbiased estimators. And this is not feasible if one or more of these assumptions do not hold. So Gauss-Markov theorem states three properties especially. First is linearity, that is beta 2 hat is a linear function of random variable such as the dependent variable y in the regression model. Then the second characteristic is unbiasedness, that is the estimated beta 2 hat. The expected value of the estimated beta 2 hat is equal to population parameter, that is beta 2. That is the sample is a appropriate or exact replica of the population. Efficiency, it means beta 2 hat has the minimum variance in the class of all such linear unbiased estimators. If these three properties are satisfied, then beta 2 hat is best linear unbiased estimators of beta 2, or what we say as beta 2 hat is blue beta 2. So if you want to try prove this Gauss-Markov theorem, and you can see, we know that beta 2 hat is equal to summation xi yi divided by summation xi square from the derivation of the econometric parameters using the ordinary least squares technique. Now, if you just try to convert, we expand the numerator of the above equation, that is in place of small yi, that is in deviation form, which is capital yi minus capital pi bar, and multiply the sum xi into terms that is within the bracket and rearrange the terms, then we'll arrive at summation xi yi small y is equal to summation xi capital Y. And we can write this equation 1 as follows as well. Since we can write this as summation xi yi, we can also write beta 2 hat equal to summation xi yi divided by summation xi square, and then summation ki yi. Just if I can annotate it a little. So if you can see, beta 2 hat becomes summation xi capital Y summation xi square. So we will consider summation x is simply xi divided by summation xi square equal to ki. We can write this equation as summation ki capital Y. This shows that beta 2 hat, this shows that this shows that beta 2 hat, beta 2 hat is a linear estimator because it is a linear function of yi. It is weighted average of yi with ki bits. So now, if you just try to prove the properties, unbiasedness property, we have to make some assumptions, or we have to derive some properties of ki. Since xi are assumed to be non-stochastic, their ki are non-stochastic too. Summation of ki, that is summation of xi upon summation of xi square, would be equal to 0. This is how, because the deviation of actual observation, sum of the deviations of actual observations from its side is 0 divided by 0. Summation of ki square will also be equal to summation 1 by summation xi square. Summation ki xi is nothing but equal to 1. If these are the properties of ki, then we can prove the unbiasedness property based on this, that beta 2 hat is summation ki yi, and it is reduces to beta 2 summation ki yi. And when we take expectations on both sides, since assumption 3 states the expectation of ui is equal to 0, so the second term cancels out and expectation of beta 2 hat is equal to the population parameter beta 2. So this becomes proof of the unbiasedness. And for the best property, that is the beta 2 has the minimum variance, we can say, know that in the first step beta 2 hat equals summation ki. And let us say we consider a alternative linear estimator, that is beta 2 star. That is in place of ki, we consider here a weight called wi, and wi is not necessarily equal to ki. So if you just find out the expected value of beta 2 star, we will arrive at beta 1 summation wi, beta 2 summation wi. Therefore, for beta 2 star to be unbiased, we must have summation wi equal to 0 and summation wi x equal to 1, which is equivalent to the property of ki. Since the last term in equation 5 is constant, variance of beta 2 star can be minimized only by manipulating first term. If we let summation wi equal to xi by summation xi square, it reduces to variance of beta 2 star equal to variance of beta 2 part. In other words, with weights wi equal to ki, which are the least square weights, the variance of the linear estimator beta 2 star is equal to the variance of the least square estimator beta 2 hat. Otherwise, variance of beta 2 star, that is the alternative estimator, is greater than variance of beta 2 hat, because there is this added term, that is beta 1 summation wi. So this proves that our the beta 2 hat is the linear unbiased and it has the minimum potential as of all estimators. That is why the Wales estimator of beta 2 hat is unbiased, linear, and has the minimum variance. So thank you all.